Today we are going to discuss about some problems related to the minor losses. Right, first problem, please note down. Find the loss of head when a pipe of diameter 200 mm is suddenly enlarged to a diameter of 400 mm. The rate of flow of water through pipe is 250 liters per second. This is the given problem. Here the diameter of the pipe is 200 mm, D equal to 200 mm. This is suddenly enlarged to a diameter of 400 mm. Diameter D1, initial diameter, that is enlarged to 400 mm, that is D2. And rate of flow is also given, Q equal to 250 liters per second. 250 liters per second. Find the head loss. Right here, based on this problem, the diameter changes from 200 mm to 400 mm. The corresponding head loss is known as, that is the minor head loss, that is due to expansion or enlargement. Head loss due to enlargement HE equal to, I have already derived one formula, that is V1 minus V2 square divided by 2G. Right, in this problem they have given discharge 250 liters per second, diameter D1 and diameter D2. Right here, this is one pipeline. The diameter is 200 mm, that is enlarged to a diameter of 400 mm. Right, this is equal to D1, this is equal to D2. But for the determination of head loss due to expansion or head loss due to enlargement, HE is equal to V1 minus V2 square divided by 2G. V1 and V2 are not given directly. For the determination of V1 and V2, they have given diameter at section 11. This is section 11. This is section 22. And the diameter at section 22 and discharge is given. Now we are going to determine the velocity at section 11. For the determination of velocity, we know one standard formula, that is Q equal to AV. Now we are going to determine the velocity at section 11. Therefore, Q is equal to A1 V1. Right? Q is equal to A1 V1. Therefore, V1 is equal to Q divided by A1. Okay. What is the Q? Q is given, the discharge from the pipe is given, that is 250 liters per second. First this converts into meter cube per second. 250 liters per second, 250 into 10 power minus 3 meter cube per second. This discharge is given in liters per second, that is converted into meter cube per second. Therefore, 250 into 10 power minus 3 meter cube per second. Discharge is equal to 250 into 10 power minus 3 divided by area. What is the area formula? That is equal to pi D1 square divided by 4. This is equal to 250 into 10 power minus 3 divided by pi into, what is the diameter at section 11? 200 mm, that is equal to 0.2 meters, so square divided by 4. Then we have the velocity V1 at section 11, that is equal to 7.96 meter per second. Now we have determined here the velocity at section 11 equal to 7.96 meter per second. Now we are going to determine the velocity at section 22. Here also same formula. We are going to use same formula. Q is equal to, now Q is equal to A2 V2. Q is equal to A to V2, therefore V2 equal to Q divided by A2, right? This is equal to, same, what is the Q value? 250 into 10 power minus 3 divided by pi into, what is the diameter at section 22? Diameter at section 22 equal to 400 mm, that is equal to 0.4 meters so square divided by 4. Therefore, V2 is equal to 1.99 meter per second. This is the velocity at section 22. This is the velocity at section 11. Now we are going to substitute the values V1 and V2 in the standard equation. Therefore, head loss due to friction, HE is equal to, what is the V1? V1 is equal to 7.96 minus what is the V2? 1.99 square divided by 2g. 2 into g is 9.81. Finally, head loss due to friction equal to 1.816 meters of water. This is the problem. Finally, we have determined head loss due to enlargement equal to V1 minus V2 square by 2g. V1 is equal to 7.96 minus V2 is equal to 1.99 whole square divided by 2 into 9.81 g value. Finally, we have the head loss due to enlargement equal to 1.816 meters of water. Right. Now we are going to discuss one more problem related to the minor losses. Please note down the problem. At a sudden enlargement of water main from 240 mm to 480 mm diameter, the hydraulic gradient raised by 10 mm, find the rate of flow. Here they have given that one water main, that is the diameter varies from 240 mm to 480 mm and the hydraulic gradient raised by 10 mm, find the rate of flow. Right here, the initial diameter is given, that is equal to, D1 is equal to 240 mm, and enlarged diameter D2 is equal to given, that is equal to 480 mm. Find the rate of flow, Q is equal to what? Now, this is pipe diameter, the initial diameter, that is 240 mm, that the diameter is enlarged to 240 to 480 mm. Right here, this is the data given in the problem. Apart from that, hydraulic gradient raised by 10 mm. Before going to solve the problem, we should know what is hydraulic gradient line. Hydraulic gradient line means is the pressure head and datum head at one section. Suppose this is section 11, this is section 22. The pressure head at section 11, the hydraulic gradient line at section 11 equal to pressure head at section 11 P1 by W plus Z1, that is the datum at section 11. This is the hydraulic gradient line at section 11. Hydraulic gradient line at section 22 is equal to P2 by W plus Z2. This is the hydraulic gradient line at section 22. Hydraulic gradient line at section 11. Now in this problem, they have given the hydraulic gradient line raised by 10 mm. That means, first we should know Here the diameter of the pipe is 240 mm. At section 2.2, the diameter of the pipe is 480 mm. Here the cross-sectional area is increased here as compared with at section 1.1. Once the cross-sectional area increases, automatically pressure head is more. Cross-sectional area is more, pressure head is more, because the velocity is less at section 2.2. At section 1.1, cross-sectional area is less, velocity is more, pressure head is less. So that based on this Bernoulli equation states that pressure head plus velocity head plus datum head at section 1 must be equal to pressure head plus velocity head plus datum head at section 2.2. Based on that statement, the pressure head is more here, automatically pressure head is less here. But in this problem they have given the hydraulic gradient line raised by 10 mm. That means the pressure head at section 2.2 minus pressure head at section 1.1 is equal to the difference between these two pressure heads or the difference between these two hydraulic gradient lines equal to 10 mm. Right? Therefore, P2 by W plus Z2 minus P1 by W plus Z1 is equal to 10 mm. That means 10 mm first that converts into meters. 10 mm means 10 mm divided by 1000, that is the meters, 0, 0 cancel, that is equal to 1 by 100. Therefore, P2 by W plus Z2, hydraulic gradient line at section 2.2 minus hydraulic gradient line at section 1.1 is equal to 10 mm, that is equal to 1 by 100 meters. This is equal to 1 by 100 meters, right? This is the relation between these two. We want to determine the discharge Q in this pipeline. For the determination of discharge Q, we know one formula, Q is equal to A V, or Q is equal to A1 V1, that is equal to A2 V2 based on the continuity equation. The discharge is constant at section 1.1, that is equal to section 2.2. We are going to use any one formula for the determination of the discharge, that is A1 V1 or A2 V2. But in this case, only they have given diameters at section 1.1 and diameter at section 2.2, but we don't know the velocity at section 1.1 and velocity at section 2.2. For that, first we are going to determine the velocities at section 1.1 and section 2.2, so that here we are going to apply Bernoulli's equation at section 1.1 and section 2.2. Right? What is the Bernoulli's equation? The pressure head plus velocity head plus datum head at section 1.1 must be equal to pressure head plus velocity head plus datum head at section 2.2. Based on that statement, the pressure head at section 1.1 P1 by W plus datum head plus velocity head at section 1.1 V1 square by 2G is equal to pressure head at section 2.2 P2 by W plus Z2 is the datum head plus V2 square by 2G velocity head at section 2.2, plus there is a head loss due to sudden expansion. The diameter is changing from 240 mm to 480 mm. Therefore, this is the flow direction. Automatically, the head loss because of the sudden expansion, that is plus head loss due to sudden expansion here. Okay, this is the relation based on the Bernoulli's equation. Now P1 by W plus Z1 V1 square by 2G is equal to P2 by W plus Z2 plus V2 square by 2G plus HE. This expression can be written as P2 by W plus Z2 minus, this is moving other side. That means P1 by W plus Z1 is equal to all these terms are moving this side, that is v2 square by 2g and he, right? Now this is equal to v1 square by 2g minus v2 square by 2g minus he, right? Now P2 by W plus Z2 minus P1 by W plus Z1 is known as, already we have derived here based on the hydraulic gradient line, this is equal to 1 by 100. 1 by 100. 1 by 100 is equal to V1 square by 2G minus V2 square by 2G minus HE. Now we are going to develop the relation between the velocity at section 11 and velocity at section 22. Right, now we are going to apply continuity equation. What is the continuity equation? The cross-sectional area into velocity at section 11 must be equal to cross-sectional area into velocity at section 22. Therefore, A1 V1 is equal to A2 V2. Therefore, V1 is equal to A2 V2 divided by A1. Okay. Now, V1 equal to, what is A2? A2 is nothing but pi. A2 means that is the cross pi d square. D is taken at a diameter at section 22. Diameter at section 22, that is equal to pi into d square, that is equal to 480 mm square, pi d square divided by 4 into V2 divided by A1. A1 is equal to pi into d, that means cross sectional area at section 11 diameter is equal to 240 square divided by 4. Right, now 4 gets cancelled, 4 cancel, pi cancel, right? Now this is equal to, V1 is equal to 480 divided by 240 square into V2. 0 cancel, 1 2, that is equal to V1 is equal to 4V2. The relation between the velocity at section 11 and then velocity at section 22, therefore V1 equal to 4V2. This is the relation we have. Now this value is substituted here. Then we are going to find the, now we are going to the value V1 is equal to 4V2 in this equation. This is equal to 1 by 100 equal to V1, in place of V1, 4V2 square divided by 2G minus V2 is V2 square by 2G minus HE is equal to what? Head loss due to enlargement. I have already given the V1 minus V2 square divided by 2G. Now in place of V1, this is equal to 416 V2 square divided by 2G minus V2 square by 2G minus, in place of V1 we are going to take 4V2 minus V2 square divided by 2G. 1 by 100 is equal to 16 V2 square by 2G minus V2 square by 2G. This is 4V2 minus V2, 3V2, 3 square, 9V2 square by 2G minus 9V2 square divided by 2G. Right, now all parameters known, only unknown is V2. Right, 1 by 100 equal to 16, all are common values, 2G 16 minus V square minus 9 minus 1 minus 9 minus 10, 16 minus 10 equal to 6 V square divided by 2G. 6 V square divided by 2G. Therefore 2G is equal to 100 into 6 into V square. Now V equal to square root of 2G. 2 into 9.81. G is nothing but 9.81 acceleration due to gravity, divided by 100 into 6. Therefore, V2 is equal to 0.181 meter per second. Now we have determined the velocity at section 2 equal to 0.181 meter per second. Now, based on this value, we are going to determine the discharge at section 1 or at section 2. For the determination of discharge at section 1, therefore V1 is equal to 4V2. V2 is known to us. Then we are going to determine the V1. Otherwise, we are going to use any formula. That means Q is equal to A1 V1 equal to A2 V2. Any formula, A1 V1 or A2 V2, any formula gives the same value. Therefore, we are going to take Q is equal to A2 V2. Right? What is A2? That is equal to pi area at section 2. Pi, what is the diameter? 480 mm, that is equal to 0.48 meter square, pi d square divided by 4 into what is the velocity V2? V2 equal to 0.181. Finally, discharge Q is equal to 0.032 meter cube per second. This is the discharge determined here. Now we are going to discuss about one more problem related to the minor losses. Please note down. Please note down the problem. Water is flowing through a horizontal pipe of diameter 200 mm at a velocity of 2 meter per second. Water is flowing through a horizontal pipe of diameter 200 mm at a velocity of 2 meter per second. A circular solid plate of diameter 150 mm is placed in the pipe to obstruct the flow. Find the loss of head due to obstruction in the pipe. Coefficient of contraction equal to 0.62. Right. Here in this problem, they have given the diameter of pipe D is equal to 200 mm and in this pipeline, suppose this is the pipe, the diameter equal to 200 mm. In this pipeline, an obstruction that is the dia equal to 150 mm. The water is flowing through this pipe. Find the head loss due to obstruction. Right, obstruction diameter D equal to 150 mm, diameter of the pipe equal to 200 mm. Here, for the determination of head loss due to obstruction, already I have given one formula, that is head loss due to obstruction equal to V square by 2G, bracket begin, capital A divided by coefficient of contraction into capital A minus small a minus 1 whole square. This is the formula for the determination of head loss due to obstruction. Right here, A is the cross-sectional area of the pipe, small a is the cross-sectional area of the obstruction. Coefficient of contraction CC is given, that is equal to coefficient of contraction is equal to 0.62. And also velocity of flow in the pipe is also given, that is equal to V is equal to velocity of flow is equal to 2 meter per second. In this problem, they have given velocity, diameter of the pipeline given. Based on the diameter, we are going to determine the cross-sectional area of the pipe. Diameter of the obstruction given. Based on that diameter, we are going to determine the cross-sectional area of the obstruction. Right? Now, first we are going to determine area of the pipe is equal to, that is equal to formula pi d square by 4, that is equal to pi into what is the diameter? Diameter of the pipe equal to 200 mm, that is equal to 0.2 meters. d square, pi into 0.2 square divided by 4. Right, cross-sectional area of the pipe A is equal to pi d square by 4, pi into d is equal to 0.2 meter square divided by 4, that is equal to cross-sectional area 0.031 meter square. Now we are going to determine the cross-sectional area of the obstruction. That is equal to same formula, pi d square by 4. Here diameter is the obstruction diameter. That is equal to pi into what is the diameter? 150 mm. That is equal to 0.15 square divided by 4. Therefore, area of the obstruction is equal to 0.0176 meter square. Now we have determined area of the pipe and area of the obstruction. Now these values are substituted in the standard equation. Now head loss due to obstruction is equal to velocity. What is the velocity? 2 meter per second. 2 square divided by 2 into g value is 9.81, bracket begin, cross-sectional area of the pipe equal to 0.031 divided by coefficient of contraction that is given in the problem, that is equal to 0.62. Then cross-sectional area of the pipe, that is equal to 0.031 minus cross-sectional area of the obstruction, that is 0.0176 minus 1 whole square. This is the formula. Finally, all are known values. Finally, head loss due to obstruction is equal to 3.311 meters. This is the head loss due to obstruction. Right? Now we are going to discuss one problem related to the pipes are connected in series. Please note down the problem. 3 pipes of length 800 meters, 500 meters and 450 meters and of diameters 500 meters, 400 meters and 300 meters respectively are connected in series. 3 pipes are to be replaced by a single pipe of length 1700 meters. Find the diameter of the single pipe. What is the diameter of the single pipe? In this problem, they have given 3 different lengths of the pipes and 3 different diameters of the pipes that are connected in series. And also in this problem, they asked that 3 pipes are to be replaced by a single pipe of length 1700 meters. So what is the diameter required? As per the equivalent pipelines, the formula for the equivalent pipes, L divided by D equal to L1 by D1 power 5 plus L2 by D2 power 5 plus L3 by D3 power 5. This is the formula as per the equivalent pipes definition. Right. So here one pipe of diameter, one pipe of length 800 meters and diameter 500 mm. And another pipe 500 meters and diameter 400 mm. This is another pipe, diameter 400 mm, length 500 meters. And one more pipe, length 400 meters, diameter 300 meters. This is the one more pipe, length is 400 meters and diameter is 300 mm. That means this is the L1, this is L2, this is L3. Pipe 1, pipe 2, pipe 3 connected in series. Right, diameter of pipe 1 is 500, that is nothing but D1. Diameter of pipe 2, that is 400, that is equal to D2 equal to 400 mm. And diameter of the pipe 3, that is equal to D3 is equal to 300 mm. 300 mm. Now all values are known to us. L1 known to us, L2 also known to us, L3 also known, D1, D2, D3, all parameters are known, and also equivalent pipe length is also given in the problem, that is equal to 1700 meters. Only unknown is diameter. Only unknown is diameter of the equivalent pipe. Now we are going to substitute the all known values here. Finally, we are going to determine the diameter of the pipe, equivalent pipe. Right. L, what is the L? 1700. 1700 divided by D is equal to L1, 800 meters divided by, what is the diameter D1? 500 mm. That means 50 centimeters. That is equal to 0.5 meters. Whole power 5 plus L2. L2 is 500 meters divided by D2. D2 is 400 mm, 40 centimeters, 0.4 meters. 0.4 power 5. And last pipe, the length is 400 meters and diameter is 300 mm, that is equal to 0.3 meters, so whole power 5. All are known values. Only unknown is D. Therefore, the diameter of the equivalent pipe D is equal to, from this equation, right. Therefore, the diameter D from this equation, D equal to 0.3714 meters. This is the equivalent pipe diameter, diameter of the pipe equal to 3714 mm. Then this converts into mm, that is equal to 371 mm. So here one pipe 500 mm, another pipe 400 mm, another pipe 300 mm. The equivalent pipe diameter is equal to 371 mm. Right? This is the problem related to pipes are connected in series. Right? Thank you. Thank you one and all.